Hello class, welcome to Geometry Lesson 9.2, Proofs Using Coordinate Geometry. So our essential question today is, how can geometric relationships be proven algebraically in the coordinate plane? And our goal is to prove geometric theorems using algebra in the coordinate plane. So we're going to talk about writing coordinate proofs, what we call coordinate proofs. Now to plan and write a coordinate proof, first thing you want to do is determine which measures or numerical relationships you must find to show the statement is true. And this is sort of like the planning stage. You want to draw and label a figure on a coordinate plane, choosing coordinates that simplify the calculations. So for example, you generally want one of the vertices of a given shape to be at the origin. So make the diagram conducive and easy for you to do the proof. Find or compute the measures needed to prove the statement, and that's the execute proving step. So once you do that and you prove the statement by computing the measures, then you're done with the proof. So for example 1, we want to write a coordinate proof of the trapezoid mid-segment theorem. So because you probably don't remember that theorem, I went ahead and included it here. So the trapezoid mid-segment theorem is, if you're given a trapezoid and you have a line segment that connects two legs of the trapezoid such that the two endpoints of the line segment are the midpoints of the legs, then you have what is called a mid-segment, xy, and that mid-segment is in such a way that the average, or the length of that mid-segment, is equal to the average of the two bases of that trapezoid. So you add the two distances of the bases and then divide them by 2. And that's going to be the length of this, okay? And that's the trapezoid mid-segment theorem. All right, so let's go ahead and prove that theorem. So in order to prove this, remember, we're going to have to construct a trapezoid. And going back to the diagram, we're going to have to compute the length. So we need the distance of that. We're going to need to calculate the midpoint here, so that we know what the midpoint coordinates are, and then find that distance, and then calculate these distances to see if we average them, it'll equal that distance, okay? So there's a bunch of things that we got to do here, so let's go ahead and do it. So we're going to construct a coordinate system where the trapezoid, or one corner of the trapezoid, one vertex, is in the origin. Okay, so this is our coordinate plane. Let's make it so that one of the corners, one of the vertices of the trapezoid is in the origin. We'll call that point A, and that's 0, 0. Let's go ahead and draw the rest of the trapezoid. It doesn't really matter how it looks like. Let's call that point B, point C, and we have here point D. Let's connect them in a trapezoid. And let's say that B, capital coordinates of point capital B, is a little a away and little b up. And let's say that point C is little c away and little b up. So that's going to be little c and then little b. Capital B is going to be lowercase a, lowercase b. And that's the coordinates of capital B, capital C. Then let's do the coordinates of capital D. Let's say that capital D is lowercase little d, so lowercase d away. So it's going to be lowercase d and then 0. Okay, so we got all the coordinates. And then generally in these proofs, you're not going to have numbers, you're just going to have variables like this. So we need to construct a mid-segment here. So we need to figure out the mid-segment for this trapezoid. And let's call those points E and F. And we're going to calculate E and F. That's the first thing that we're going to do. So let's go ahead and first, let me zoom in on this first. So first we're going to connect this with a line segment. Let's use the same color. Well, I was going to use a different color. Let's use the same color. So we got EF, and let's calculate the coordinates of E first, which remember we got to do the midpoint formula. The midpoint formula states that you add the x coordinates divided by 2. You average the x coordinates. So it's going to be a plus 0 divided by 2. Then you got to average the y coordinates, divide that by 2. So b plus 0 over 2. Now a plus 0 is just a. It doesn't really do anything to a because it's 0. 0 doesn't do anything to the number. So you got a over 2 and b over 2. And that's the coordinates of E. Let's do the coordinates of F. It's going to be the average of the x coordinates there, C and D. So you got to do C plus D divided by 2. And then the average of these coordinates, so B plus 0 divided by 2. And C plus D is just going to be C plus D. There's nothing you can do with that. Over 2. B plus 0, however, is B. Okay, so those are my coordinates of E and F. So now let's go ahead and show that this is a trapezoid by doing the slopes, right? Well, we know that the slope of BC is 0, and that's because it's completely flat. The rise is 0. Same thing for the slope of AD. The slope of AD is 0. So we know that these are parallel, and therefore it's a trapezoid. We also know that the slopes of AB and CD are not the same. So the slope of AB is rise, which is B, over run, which is A. And that's not equal to the slope of CD, which the slope of CD is down. You got to go down C, or down B rather, sorry, down B and over C. And over C minus D rather, you got to go over this little tiny amount, which is that D minus C. So we know it's not the same thing because you got to go down B, but you got to go over C minus, or D minus C. Like if D were 5 and C were 4, then you got to go over 4, 5 minus 4, D minus C. And that's not the same thing as B over A. In fact, this is going down B, which is negative. So this is a trapezoid, okay? So we got a trapezoid, we got the mid-segment right here, the mid-segment. Now we want to show that the length of the mid-segment is equal to the average of the BC and AD. So let's calculate the distance of BC. Distance of BC is BC is between A and C, right? So you got to subtract C minus A, and that'll give you the distance between B and C. So you got to do lowercase c minus lowercase a. So if C were 10, A were like 7, they'd be 10 minus 7 or 3. And then let's do the distance from A to D, which is lowercase d minus 0. So AD is just D. Okay, so we got the distance of AD and BC. So now let me do this in another color. So we got, this is distance C minus A, oops. C minus D. This is the distance of, or C minus A rather. And this is the distance of D. Now we want to average those two numbers together. So we got to do A, D. So we got to do that. So these two purple ones, this one and this one, we got to average those two. AD plus BC divided by 2, okay, and that should give us EF. So AD is D, lowercase d, and BC is C minus A over 2. Okay, so that's our average, and that should be equal to EF. So let's calculate EF now, and let's do a different color for EF so that we're not confusing ourselves with all this, all the calculations here. Okay, so that should be equal to EF. So let's calculate EF. Now the distance from E to F is, well, we know the coordinates of E is A over 2, right? So you got to subtract the coordinates in the x direction. So you got to subtract this coordinate from this coordinate and this coordinate from this coordinate. But B over 2 minus B over 2 is just 0, so it goes away. You can just ignore it. So what's the distance from this to this? You just got to subtract them. C plus D over 2 minus A over 2. And if you remember, when you subtract a fraction, you just keep you got to subtract, you have to have a common denominator, and we do. So the common denominator is 2, and then just subtract the numerator. So we got C plus D minus A. Now let's compare that to this. those are the same exact thing. It's just a rearrangement, right? They just switch C and D together. So those are equal. So that means that this is equal to EF, and that is true, and that is the end of the proof. If I average these two sides, it's the same exact thing as if I find a distance, EF. Okay, so these kind of theorems, there's a lot of calculations involved, a lot of variables, so they tend to be a little on the harder side. Let's do a coordinate proof of the following. A point on the perpendicular bisector of a segment is equidistant from the endpoints. So essentially what we're trying to prove here is the perpendicular bisector theorem, which states that if you have, a line segment and you have a perpendicular bisector. Perpendicular bisector means it's 90 degrees and it cuts it in half. So this is 90 degrees cutting this segment in half. And they're saying that if you're here on this perpendicular bisector, is the same distance here as it is here. So between these endpoints. So we're going to prove that. So we're going to draw a diagram kind of like that. Let's go ahead and draw our diagram. So we got our X and our Y. And this time actually what we're going to do is we're going to draw it kind of symmetrical, where we have point A on the line segment there, point B on the line segment here. The perpendicular bisector cuts it in half right here at the origin. We'll call that point C. And then we'll call this point D for the other part of this perpendicular bisector. So this here is the perpendicular bisector. And then AB is the line segment. Okay, so that means this is getting cut in half. So we want to show that that's the case. So we got let's say the distance from C to B is, let's call that lowercase. Yeah, let's call it lowercase a. And this is lowercase a. So that means that this is negative a and 0 because it's going to the left. And B has to be going positive a and 0 and going to the right. And let's call this distance here, let's call that distance B, lowercase b. So that means the capital D is lowercase 0 and then, or 0 and then lowercase b because it's going up. All right, so now let's see if this distance is the same as this distance, okay? We got to prove that that's congruent. Okay, so, and we know that this is a right angle. Okay, so first off, how do I know that it's a right angle? Because we got a vertical line and a horizontal line. So I constructed this so that it is perpendicular. All right, let's calculate the distance from D to B. Distance from D to B. It's going to be the distance formula. So I got to do the horizontal change, which is A, squared, plus the vertical change, which is B squared. So remember, the square root of the horizontal change plus the vertical change. And that's my distance dB. And let's go ahead and do dA. So dA is the distance formula, and it's still going to be A, right? Here, just because I showed that it's the same distance because it's a midpoint. C is the midpoint, so it's the same distance on both sides. So it's still going to be negative A squared, though, negative because it's going to the left. And then, so we'll put this negative. And then it's going up by the same amount, B squared. Now, it doesn't matter if it's negative. A negative squared is the same thing as a positive squared. So this is the same thing as positive A squared plus B squared. Which means that dA is equal to dB. And that's true. Which means a point on the perpendicular bisector, this is the perpendicular bisector DC, which is point D right here, a point D, is equidistant, the same distance, from the end of the line segment. So the endpoints are A and B. So we just proved that this is correct. So let's go ahead and finish up with one more example of a coordinate proof. So we got the diagonals of a kite are perpendicular. So let's go ahead and draw ourselves a kite. Let's say this is point A at 0, 0. This is point B, point C, point D, capital D. And let's say that B is A away from the origin and B away from the origin and the Y. And so the coordinates of capital B are lowercase a, lowercase b. And the coordinates of D are lowercase a, lowercase negative b, because it's on the other side and it's symmetric. And then the coordinates of C, capital C, are, let's just say that it's lowercase c away. So it's lowercase c and then 0. And let's make sure that this is capital C so we won't confuse that with the lowercase c. All right, so now we got our coordinates. Let's go ahead and do the diagonals of the kite. So we got this diagonal and this diagonal. So we want to prove that those are perpendicular. All right, so in order to prove that those are perpendicular, well, first off, we need to show that this is a kite, and that's not, you know, hard to do. The distance from A to B is a squared plus b squared, right? So this is a squared plus b squared. And the distance from here to here is square root of negative b squared and then a squared. So it's square root of a squared plus negative b squared. So these are the same thing. And then the distance from capital B to capital C, well, it's the distance from A to C is C minus A. You got to subtract those two numbers. The distance from up here, from this up, is b minus, it's just b. So the distance here is square root of b squared and then c minus a squared. And then same thing here, c minus a, and then this is negative b. So it's going to be a square root of negative b squared plus c minus a squared, which is the same thing. So these are the same distance. So I was trying to make it so that it's the same distance. So clearly they're the same distance. Let's go ahead and do the diagonals. Let's do the slope. So the slope of BD in purple, it's rise or run. How much does it rise? Well, it rises from D to B. It goes up. So it goes up B and then another B. So we just subtract these two coordinates. So rise over and then run, you got to subtract those. A minus A is 0. So two negatives is a positive, so we got b plus b is 2b, a minus a is 0. 2b divided by 0 is undefined. This is actually, you can't actually calculate, you can't actually divide by 0. You get what we call an infinite slope, which this proves that this is a vertical line. Any line that has an undefined slope is a vertical line, okay? Now let's calculate the red slope AC. So this is the slope of BD. Now let's do the slope of AC. We're not doing distance, we're doing slope. So this should be a little BD. So the distance here, you got to do rise or run. So the rise is 0 because you're in flat terrain here. You're not climbing at all. So it's going to be 0 minus 0. The run is C minus 0. So you got 0 divided by C, 0 divided by any number that is not 0 is 0. If you got a slope of 0, that means that you got a horizontal line. So a horizontal line and a vertical line are always perpendicular. Horizontal plus vertical lines are perpendicular. So therefore we've shown that this is perpendicular, that's a right angle. So the diagonals of a kite are perpendicular. All right, that's gonna do it for the video, guys. I hope you found this useful. I hope you took a few things. Like I said, this example, this lesson is a little bit on the hard side with the variables, but it just takes practice in order to prove various theorems. Set up a coordinate plane like we did, make the calculations kind of simple for yourselves, label variables for every coordinate, and then use the distance formula, slope, and so on. All right, guys, take care. Have a great rest of your day.